Hello! In the last video, we solved the heat equation and we came up with this series to describe how the heat moved in the sword with ice in both ends and with an initial heat distribution that it was proportional to the length of the sword, right? It was just equal to x. Today I want to show you how this series looks in time and space, because that is really important. When Fourier solved this series, and when he saw what I'm about to show you, he realized that, he knew that the solution to the heat equations, that he had found a way to solve the heat equation, and he knew that it was important. But when he saw the properties of the solution, he realized that the properties were even more important. So for starters, I finally got around to making that integral is this integral over here. Yeah, we have the 2 over L. I don't know why you put it inside the integral, but doesn't matter. And then x times sine. And we got this, right? Well, you can see that since n is a whole number, but Wolfram alpha doesn't know it, this part is 0. And we can cancel p, the squares, with these 2 in here. So this can be simplified to a much simpler equation. And the thing is that I actually made a simple program to show you how it looks like. Right? This is MATLAB. Don't worry if you don't know how the code works. This is not about the code, but I want to show you how it looks like. So, for example, here I have this code, and all you have to know about this code is that this code will make a series, right? Will make actually the Fourier series. So, for example, this means that it's going to take the first 300 terms. Remember that I told you that, well, the Fourier series goes up to infinity, but we cannot do it up to infinity. So we have to pick a big number and use it, right? And so this is going to work in a linear space. Here I'm just using the length of the sword will be equal to 1 unit, 1 meter if you will. And this means that I'm going to plot the equation just in the sword, right? And well, let me show you how it works. So this is how the distribution would look at first. As you can see, it's pretty much just equal to x, right? As we saw. But here it starts looking different. This is no longer just x. Well, this happens because we are not taking all the terms, because we are just taking a part of the Fourier series. So what we are getting is just an approximation. But as you can see in all these places, it's a very good approximation, and it only stops failing just near one of the ends of the sword, right? This would be like the hilt or whatever. But this is if I take 300 terms of the Fourier series. Well, let's see how it looks if I take even less terms of the Fourier series. As you can see, it begins looking more and more squiggly. Yeah, you remember that I told you that it would look more squiggly. Where was the drawing? Yeah, over here, right? Remember that I told you that it would look kind of squiggly, and as we take less and less terms, it will look less and less like just equal to x. Here now you can see that we have here like a fall, right? Alright, so maybe maybe this one looks actually, I put 500 terms instead of 50. I wanted to take just 50. I was thinking, oh, what does it look better, the approximation? Yeah, with 50 terms it looks less even good, and let's just go like for an extreme and take just like 3 terms. This looks nothing like x, but as we take more terms and more terms, you can see how it approximates better the solution if you take 10 terms, and if you take 15 terms of the Fourier series, it starts looking decently. If you take 30 terms, you can actually like almost see where it's supposed to be. If you take like 40 terms, and so on. Oh well, so this is how the Fourier series looks at first, right? In the initial state when x is equal to 0. Now let's look how it looks when it changes in time. Just don't worry about this code in here, but what this code will do is that it will show you how how the heat equation looks in the sword at different points in time. So let's look at that. Oh, perhaps that was too fast. Let me just slow it down a sec. Oh, where is it? Ah, sorry for that. Yeah, here. Alright. So that was too fast. I should just put just 1 second in here. Alright. So this is why you should try to rehearse a little. So let me see. I think this is a problem. This shouldn't go all the way up to 300 seconds. This should go all the way up to 1 second. Yeah, now it should look better. So as you can see, the equation began pretty similar to just equal to x, but as time goes on, it changes. See? And it goes low and low and low, and it takes a while. Let's look at that again, alright? Shall we? So first, I'm taking just 1 second because otherwise it would be too much. And now a little faster so that it looks a little smoother. Yeah, you can see this kind of jumps that the series makes is because the graph is adjusting to the size of the equation. But as you can see, the equation went from being pretty much equal to x to now it's just a parabolic equation, something like with an x squared, right? Which is interesting because that tells us that the heat that was concentrated most in one side of the sword at first, it's going to go to the left, and is going to eventually one of the sides will go to 0 as we had chosen with one of our boundary conditions, and the heat will eventually be like evenly distributed all along the sword. And even I'm gonna take just a larger span of time. I'm gonna take 10 seconds, and I'm going to take just 300 in here because I want you to see something. And that is that, well, here the initial condition lasted so little that we couldn't even see it. But as you can see, eventually it doesn't change anymore. It reaches like an stable state. Granted, the temperature goes lower and lower, as you can see by this exponent. I don't know if you can read it. But the thing is that it behaves like real temperature in the sense that it reaches an stable condition and doesn't change anymore. So Fourier saw these two things that I show you. How the series looks in space and how it looks in time. But eventually you may be wondering like, well, we can plot the equation and we are plotting it in the sword, right? From 0 to L, to the length of the sword. Here is just 1 meter. But we could plot it in a larger distance. For example, what would happen if I plotted from 0 to 10? Well, you first would tell me like, well, there's no sword there. The sword stops at 1 meter. But then I would ask you to stop thinking about the sword, about the physical representation of this, and just think about the equation. How just the equation looks when I plot it over a large over a span of space in which it isn't supposed to. Well, no, it is supposed to work in there, but we didn't come up with this equation considering this span of space. We came just considering the span of space from 0 to 10. So Fourier probably was curious about this, and he plotted this with the best technology he had at the time, and he saw the following. Oh no, sorry, what happened? This should have happened. From 0 to... oh no, this should be from 0 to L, yeah, but no. Wait, damn it. Oh, here's the problem. Yeah, so this is what Fourier saw, right? So for our sword is at 1 meter, so only this part over here is representing what we care about, right? This is our sword. But the equation continues. I mean, there's no reason for x just to be equal to the length of the sword. So we can take an equation over a longer span of space. And we get this. We get that the equation repeats itself, and even it goes below 0. And this is interesting. So let's see how this looks with less terms. Again, just like for curiosity, 50 terms. Interesting, it looks, well, it looks kind of nice, but it is because we are far away. If we take only 10 turns, yeah, you can see the squealiness of the equation. So Fourier was watching this, and he eventually realized what you probably are thinking now, that the equation just like, you can take a Fourier series for any initial condition, and the equation you get, if you plot it over a larger span of space, will repeat itself, which is a nice property. In fact, it's such a nice property that this is largely how circuits and signals work, because signals of sound are something like, they actually look something like this, right? Hey, what's happening? I should be able to draw here. No, all right. So yeah, whatever. So if, for example, if you want to transmit sound with electricity, well, you send a signal, and you want the signal to be like this, right? But you don't know how to generate the signal. So it's okay. You just take the Fourier series of the series in here, of this place, and the Fourier series you get will reproduce the signal all around. So this is useful. This is useful for generating signals for circuits. Actually, like the light in your house is probably the electricity that you can get from the wall or something. It's something like this, but it's not exactly like that because it's a Fourier series. So it kind of actually looks something like this. So every time you connect to the wall, your devices are getting a Fourier series of electricity. And the only way we know how to produce this signal is using the Fourier series. So this is just to show you that the Fourier series have very nice properties and they have many uses. And we're going to keep exploring those uses and those properties in the next videos.